So, question 12. A pump is inflating a spherical ball. The radius of the ball is increasing at a rate of 1 centimeter per second when the length of the radius is 2 meters. So the radius of the ball is increasing. So that's dr dt. That's equal to 1 centimeters when the length of the radius, when r is equal to 2. Now that's meters and centimeters, so I'll just convert everything into 1. So that's at r equal to 200. So dr dt is equal to 1 centimeter per second when the radius is 200. Now the first question, it says find the rate at which the pump is working, i.e. the rate of change of the volume. So they're asking you to find dv dt. That's what you're trying to find. Now, think about what they've given you. They've given you V is equal to the volume of a sphere is 4/3 pi r squared. So if you were to differentiate that, you would end up with dv dr. Now that's not what you're trying to find, but the 4/3 pi r cubed. Sorry. Differentiate that, you're getting 3 times 4/3 pi r squared, giving you 4 pi r squared. So dv dt is going to be equal to dv dr multiplied by dr dt. The dr is cancelled, you end up with dv dt. So you now know that dv dr is 4 pi r squared. And you know that r is equal to 1 centimeter. Sorry, dr dt is equal to 1 centimeters. So this is giving you 4 pi r squared has to be 200 because of this information at the start, right? If you're going to use 1 for your dr dt, you have to use 200 for your r. So 200 squared. 200 squared is 4. Sorry. I'm going to stare at that. This is 4 pi 200 squared. So 200 squared is 40,000 by 4 is 160. So you've got 160,000 pi centimeters cubed. The rate of change volume is in centimeters cubed, so the rate of change of volume is going to be in centimeters cubed. So that's your that's essentially part 1 answer. dv dt. Now, if the air continues to be pumped at this rate, find the rate of change of the radius when it is 5 meters in length. Now that's important because it's telling you that the rate of change at which the volume happens is going to remain constant. We worked it out for when the radius is 2. But the rate of change of volume isn't dependent on the radius. It's dependent on, for example, the airflow through the pump or the size of the pump or the size of the valve. These are all things that are going to affect the rate of change of volume in a sphere. So it's more to do with the pump than it is to do with the radius. So that's good to know that this is going to remain constant for the rest of the question. Okay, that there is remaining constant for the rest of the question. Okay, so if the air continues to be pumped at this rate, find the rate of change of the radius. So the rate of change of the radius is oops, sorry, get rid of that. The rate of change of the radius is going to be dr dt. So we've already found dr dt. We're told dr dt when the radius is 200, but now we need to find dr dt when it is 500. So how do we go about doing that? Well, in order to find dr dt, you need to we have dv dt and we have dv dr. So if we flip dv dr upside down, so let's just look at this for a second. So dr dt, that's what we're trying to get. That's going to be equal to dr and dt. So dr over dv, dv over dt. So we know dv dt, we've just worked it out over here. We told it that's constant, so we know that that is going to be equal to 160,000 centimeters cubed. And dr dv, we can take this here, sorry I rubbed it out earlier, this was dv dr. We can take this and flip it upside down. So it's 4 pi r squared, it becomes 1 over 4 pi r squared. So we multiply those two things, we'll end up with dr dt. Now, this time our r squared has got to be 500 centimeters. So it's 1 over 4 pi 500 centimeters multiplied by 160,000 pi centimeters cubed. The pi's are cancelling for us straight off the bat. 4 into that is going to give us 40,000. And 500 squared is 250,000. So all in all, 40,000 over 250,000 is the same as 4 over 25. So that's the same as 0.16. What are we finding again? We're finding the rate of change of the radius. So radius is going to be in centimeters. So 0.16 centimeters per second. And the last part of this question, at what rate is the surface area of the balloon increasing when or is equal to 5 meters? So surface area of a balloon, think about that for a second. The surface area of the balloon is given by the following formula. It's equal to 4 pi r squared. So that's area. So we would differentiate that. We're going to find the rate of change of area with respect to volume. So you're getting 8 pi r. What we need to find is the area with respect to time, not to radius. So we're trying to find dA dt. So in other words, dA dt would be equal to dA dr multiplied by dr dt. Okay, so we've got to multiply this by dr dt. So that's 8 pi r multiplied by dr dt, and we've already worked out that dr dt is equal to this over here, either of these. I'm just going to use 4 over 25. So, just to make sure it's clear, dA dr is that, and dr dt is this here, and that's why we multiply those two things. We end up getting 32 pi over 25. Sorry, we got to substitute in for r as well. So this is when the radius is at 5 meters. So you got to multiply 32 pi. 32 over 25 by, we'll go for centimeters since the rest of the question has been in centimeters, multiplied by 500. So get out your calculator, stick that in really quickly. 32 over 25 multiplied by 500, 640. 640 pi.